Good morning. We're going to be talking in this video about some calculations which we can refer to as the moment of a couple. Okay, what is a couple? A couple is a pair of parallel forces that are acting on an object that may induce some form of rotation. So let's look at our object that we've got drawn here. What we've done is draw it out based on the X, Y, and Z coordinate system. And we've labeled our axes so that Z is going up, Y is in the plane of the board, and the X is coming out. So here's our object. Now, I like to visualize the objects that I'm working with. And what I'm visualizing here is a handle for a jack. You know, maybe a handle that you lift your car with, you know, that long handle that you rotate like this to jack your car up if you've got a flat tire, or a trailer jack. This really reminds me of a trailer jack for a semi-trailer. It's shaped kind of like this. Okay, this part hooks on the trailer. This part has a little handle here, a little rotating handle so that you can rotate it around to cause the jack to turn to lift it up. So let's look at our diagram and what we've got here. So with our diagram, okay, we've got 50 newtons of force here, 50 newtons of force here, a 35 newton force and a 35 newton force. We've got some distances. We've got 850 millimeters from the origin of the axis here. We've got 1250 millimeters here. So about 0.85 meters and 1.25 meters there. So we're looking for some information that we do not have. We're looking to calculate some things. So we want to label a few points on our diagram. This would be point A. This would be point B. So what we're looking for is the distance between points A and B such that our moment is equal to 20 Newton meters. Now, what is a moment? Moment is another word for a couple, or rotation, or torque, if we want to go to that direction. So we want, excuse me, we want to see how we can calculate this out. So the moment is equal to a force acting through a position vector, R. Okay, so R times F. But really, we've got our forces. We're looking for this distance here, so we're looking for our position vector, R. Okay, so our resultant moment is equal to 20 Newton meters, which is equal to what? The sum of all of the moments in the X and the Y and the Z direction. So we're looking for that. So how can we find that? Well, we can say that 20 Newton meters is equal to the square root of the X component squared plus the Y component squared plus the Z component squared. So we've got to break it down into our components. So we've got to find mx, my, and mz. So how do we go about approaching that? Okay, now remember, a couple is two forces of equal magnitude in opposite directions. So we've got the two 35 millimeter forces, 35 Newton forces acting between A and B. One's at B and one's at A, in their opposite directions. But remember, we're having this handle, it's here, it goes up, it comes out here, it goes up like this, and it comes back out. So those two forces are not going to cause the rotation that we're concerned with 20 Newton meters. It's going to be the forces that exert here and here. Okay, so the 50 Newton forces are gonna cause that rotation, that couple that causes that moment there. So m to the x is equal to what? M to the y is equal to what? And m to the z is equal to what? That's what we want to determine. Now we know some relationships, okay? We know some relationships. We're looking at an x component, we're gonna look at m times the cosine of some angle. If we're looking for a y, that's gonna be m times the sine of some angle. And we're looking at z, we're also gonna be looking at an m times the cosine of our angle. But with a couple, what do we have to do? We have to find this, and we cannot just plug in this value here. So we need to look at it in an expanded form, so that mx is equal to the force times the distance times the cosine of our angle. My is equal to the force times the distance times the sine of our angle. And mz is equal to a force times the distance times the cosine of an angle. Now look on our diagram. I'm going to bring our diagram back down. We have an angle of 30 degrees here between this y and the point at which our handle is located. Okay, so we can plug in some information, but we've got to be mindful of what we plug in. Which forces cause rotation in the x direction, which forces cause rotation in the y direction, and which forces cause rotation in the z direction. So remember, it comes out here, it goes up, and then it comes out here. Okay, so for a rotation in the x direction, so the sum of the forces and the moments in the x direction are equal to force times the cosine of your angle. Okay? So, what force is causing the rotation in the x direction? Remember, we've got the 35 down and the 35 up. Okay? In the x direction, in the y direction, in the z direction, which is causing the rotation there. So we would have a negative 35 newtons times the cosine of our angle, which was 30 degrees. So sum of m to x is equal to this, so m to x is equal to that value there. Okay, so that's now we've got force, we've got this, we've got to include a distance. Do we know the distance there? No, that's what we're looking for. We're looking for that distance between point A and B. So we put this here. So a negative 35 times the cosine of 30 gives us what? A negative 30.31 times D. So there's mx. So if we want to do my, we've got our force times the sine of our angle times D. We still do not know our D. Our force now is not the 35, but it is the 50. Okay, so we got 50 causing that rotation, that 50 that we're exerting on the end of that handle. Okay, so it's 50 times the sine of 30 degrees times D. So the sum of our moment in the y direction is going to be equal to a negative 25 D. Now, which force is exerting, which direction is that force that's exerting that or causing that rotation with respect to y? Is it in the positive y direction or the negative y direction? Or is it causing a positive rotation or a negative rotation along that axis? Well, it's causing a negative rotation along that axis, so it'd be a negative 5, a negative 50. So we got mx and my. So we're going to solve for mz, which is f times the cosine of our angle times d, which is equal to 50 times the cosine of 30 degrees times d. So the sum of mz. Now, what direction is our rotation on around the z-axis? It's the same as around the y-axis. It's negative. So down to 30, so it's 43.33, a negative D. Now, we've got the three components here of our moment. These three components are equal to 20 newtons per meter. So we could set up our equality (30.31 d squared) plus a negative 25 d squared plus a negative 43.33 d squared. And we could solve for that so that 20 newton meters is equal to 58.5 times D. So 20 newton meters divided by 58.5, and that would be newtons. The newtons cancel would be equal to D. So 20 over 58.5 is a little bit less than a half. So it's somewhere around 0.342 meters, or 342 millimeters. So what does that tell us? Remember, moment is this, okay? So even though we're looking at the moment of a couple, our moment is at 342 millimeters, and there's a 20 newton meter resultant at that distance. So if we're looking coming out, and this distance here going up to our handle, this distance here would be 342 millimeters. So what's the difference between that and the moments that we calculated last week? Nothing. There's no difference. Okay, just because we have a couple, we have to take into account the direction of the forces. Now remember, on a couple, we have parallel equal forces in opposite direction. So if we're looking at this, only some of those forces are going to be important in making our calculations. Otherwise, they're going to cancel out because they're in equal and opposite directions, okay? So from there, we'll move on into some other calculations the next time we have class.